So we're looking at exponential functions in this lesson, where we're going to have a constant, some number, to a variable. So an exponential function is when the base, if you remember that word, the number or the thing that has an exponent on it, it's called the base. That's going to be an important word in this chapter. When the base is a constant, just a number, and the exponent is a variable, that's going to be an exponential function. And there's two main types of exponential functions based on what the base is. And so if the base is bigger than 1, that's going to be one kind of function. So we'll think, for an example, about 5 to the x. Okay? And we're going to try to figure out what this function looks like by thinking about the left side of the graph when x approaches negative infinity, like negative 10, negative 100, negative 1,000. We'll look at what's going on the y-axis, and then we'll look at the right side of the graph. So of course, the easiest thing, when x is 0, we know that anything to the 0 power is 1. So that'll be easy. We'll have y equals 1. We'll have a nice y-intercept point on the y-axis right there. Okay. Now, what about as x approaches negative infinity? So we could think about something like 5 to the negative 100th. Okay. Well, we know negative exponents make fractions. So this would be 1 over 5 to the 100th. All right, well, 5 to the 100th is a very large number. So 1 over a large number, that's going to be really, really, really small, right? So small that it's almost 0. Okay, we're going to say that y is going to approach 0. All right. Now it's never going to actually reach 0, though, right? So if x is a million, 1 over 5 to the million is going to be so small, 0.000, going on almost forever, but not quite forever. 0.0000 going on for a while. 1, really, really, really close to 0. You can get as close to 0 as you want, but never quite reaching 0. Okay. Well, what does that sound like? Getting really, really close to something, but not quite reaching it. As we go here, we get closer and closer and closer to 0, but we don't quite reach it. Well, that's an asymptote, right? What we've got here is a horizontal asymptote. On the left side, it's going to approach y equals 0, the line y equals 0, the horizontal line. Y is 0, but never quite reach it. Okay. Well, what about on the other side? As x gets really large, if you think about something like 5 to the 100th, well, 5 to the 100th is huge. So as x approaches infinity, y is going to approach infinity as well. As x gets bigger, y gets bigger. So this graph is just going to kind of shoot up here. Okay. So this exponential function, you might have heard of it before. This one is called exponential growth, because it grows. So we look at things from left to right, and it grows. It's always increasing. As x gets bigger, y gets bigger. And actually, exponential growth, you might have heard the phrase, grows exponentially. It's one of the fastest growing things that we know. This grows really quickly. This really kind of shoots up there. Okay, but that's when we have a base that's bigger than 1. What about if we have a base that's between 0 and 1? What if we have a base something kind of like 1/5? Okay, well, still we'll have the same y-intercept. When x equals 0, we'll still have y equaling 1, because anything to the 0 is 1. So we'll still have the same y-intercept. Both graphs have this y-intercept 0, 1. Okay, but now on the left and the right sides, it's going to look a little bit different. Okay, so think about 1/5 to the negative 100. Well, negative exponents make fractions. If it's already a fraction, it's going to flip the fraction. 1 over 1/5 is just 5. This is the same thing as 5 to the 100th. Well, 5 to the 100th, that's huge. So this one on the left side, as x gets more and more negative, negative 100, negative 1,000, negative 10,000, the y is actually going to get bigger. It's going to approach infinity. As x gets smaller, y gets bigger. Okay. Now on the right side, think about 1/5 to the 100th. Well, that's the same thing as 1 over 5 to the 100th. So we're back to 1 over a really large number. So this is going to be really small. It's going to be like 0.000000 going on for a while. That's again where it's going to approach 0, never quite reach it. You can get as close to 0 as you want without ever quite hitting 0. Okay? So on this one, it's on the right side when the x's get bigger, when the x's are positive, that we're going to have this horizontal asymptote approaching the horizontal line y equals 0 without ever quite reaching it. And it's going to be on the left side that it's going to shoot up like that. So this one we call exponential decay. Because again, we think of things from left to right, and decay means to get smaller, to get less. If your tooth is decaying, you're having less and less of your tooth. You're losing the enamel on your tooth. So this one from left to right, we have less and less of it. It's decaying. Okay, so exponential growth and decay based on what kind of base we have. Notice there's a few bases that we left out. If the base equaled 0 or 1, 0 to any power is 0, 1 to any power is 1. So if the base was 0 or 1, it actually wouldn't be an exponential function. It would be just a constant function, a horizontal line. And then notice we don't look at negative bases. A negative base actually behaves really, really weird. If you try graphing it in your calculator, if you try graphing something like y equals -2 to the x in your calculator, it's actually not going to show you anything. But if you try to trace, you'll be able to find some points. Something like that actually has an infinite number of holes in the graph and an infinite number of points in the. It's really weird. We just kind of say let's not even try to look at that. Let's not worry about that. Those are kind of weird functions. Okay, so we're only going to look at positive bases. And so let's look at some of the common characteristics of these two different graphs here. So we already saw we had the y-intercept 0, 1. They also both have the same horizontal asymptote of y equals 0. It's just that one has it on the left and one has it on the right, but they both have that same horizontal asymptote. Both have the same domain. If you look at these from left to right, the domain is just all real numbers. You can have any number as an exponent you want. We saw yesterday what fraction exponents did. So any kind of exponent is going to work. Now the range, though, if you look, well, we don't have any negative y values. The range is starting around 0, and then it does go up forever. And then we might think about, is it a bracket or a parenthesis on 0? Of course, it would be a parenthesis because, again, we get really, really close to 0, but we can never have a point on the graph where y does equal 0. Okay. And then notice these same basic things. It doesn't necessarily matter whether this was 5 to the x or 7 to the x or even e to the x. The exact number of the base, it would just kind of determine how steep the graph was. It wouldn't really matter that much. We're just looking at, is the base bigger than 1 or is it a fraction between 0 and 1 to know what kind of basic shape of graph we have. Do make sure you remember e. Hopefully you saw that in Algebra 2. E is kind of another one of those special numbers like pi that has a decimal that goes on forever without repeating. It's the base of the natural logarithm. So we use it a lot in calculus. It's going to show up when we do compound interest. Here's one definition. If you take this expression, make x get bigger and bigger, make x approach infinity, this starts to approach e. There's other calculus definitions. But the big thing is just know that e is a number between 2 and 3. So don't get freaked out when you see e. Just like when you see pi, you can think, hey, that's a number about 3, 3.14. And when you see e, that's a number 2 point something, 2.7. That's good enough. All right, so let's try to then take those base graphs that we know now, and let's try to do transformations. That's what we'll do a lot in this class. We'll look at a base graph, we'll find the parent graph for a function, and then we'll do transformations to it, okay? And the key things are going to be the y-intercept and the horizontal asymptote. All right, so for the y-intercept, well, the y-intercept, of course, is when x equals 0, so we can just take 0 and substitute it into the equation. So we'd have 2 to the 0 minus 1, which of course is 1 minus 1, which of course is 0. So we get the point 0, 0, which on this one we could have gotten thinking about shifts. Sometimes the shifts wouldn't give it to you, but this one you could say, hey, we went down 1, and so the point 0, 1, down 1, now we're at 0, 0. Now, the horizontal asymptote, so we have to remember what it normally is. Normally, it's y equals 0. And then we went down 1. So remember the things on the outside at the end of the function are the up or down shifts. This is a shift down 1. And so if we were at y equals 0, and then we shift down 1, now we're at y equals -1. Okay. And then, of course, we can look at our base and see that it is bigger than 1. And so we know that it's going to be exponential growth. So the graph is going to be like this here. So we're going to have the horizontal asymptote just on the left side. I mean, if you draw the dashed line all the way across, it's okay. But I'll just draw the dashed line on the left side because that's where the asymptote is going to be. And then from there, just kind of draw that rough exponential growth shape. And that's really all we need. Okay. So on this one, again, we'll find the y-intercept by plugging in 0, because this one got shifted. Remember, that's left 5. X plus 5 goes with x equals -5. So if we shift the graph left, the y-intercept that we had would move off the y-axis. So we can't get it thinking about shifts. We'll just plug in 0. So if I plug in 0, I'm going to have 2 to the 5th plus 3. So 2 to the 5th is 32, plus 3, 35. So we get the 0.035. All right, now for our horizontal asymptote, there were 2 different shifts here. Okay, well, let's think about it. The left 5, so if I have this horizontal line right here, and then I shift everything left 5, well, it's still the same horizontal line, right? You can take a horizontal line, shift it left and right as much as you want. It's still the same exact horizontal line. So the left 5 doesn't change the horizontal asymptote. All right, that's not going to matter for it. What is going to matter is this plus 3. So if we had y equals 0 and we go up 3, we're at y equals 0, go up 3, and now we're at y equals 3 for our horizontal asymptote. Still have a base of 2, so it's still exponential growth. Now notice though notice the space between the y-intercept and the asymptote now. So I'm going to put my y-intercept kind of way up here, and then my horizontal asymptote kind of down there. So picture that as being 3, that as being 35, and then sketch that exponential growth and look something like that. Okay. Now this one, we did say a minute ago that we weren't going to do negative bases. Make sure you understand this is not a negative base. This one, the base is 3. This is 3 to the x. Whatever you have for the exponent, you put that exponent on 3. You do that exponent first, and then whatever you get, you stick a negative on. Okay? A negative base, we'd have to have parentheses around the base. Okay? So this one, when I find my y-intercept, I'm doing negative 3 to the 0. Listen how I said that. It's negative 3 to the 0. We have to do the exponent first before we do the negative. So 3 to the 0 is 1, and then I stick the negative on it. And so I'm going to get 0, -1. Okay? So I'm not doing negative 3 to the 0. That would be 1. So this is negative 3 to the 0. This one is negative 3 to the 0. Okay? And so then let's think about my horizontal asymptote. Well, I don't have any shifts up or down, right? All I have is this negative here, okay? So, well, this negative, that's negative y's. So I'm changing the y between negative and positive. So that would reflect about the x axis. So it makes sense now why my y-intercept is down here at 0, -1. Normally I had this y-intercept. I changed the y's between negative and positive. I reflected about the x-axis. And so now my y-intercept is down here. Okay, again, the negatives on the outside or on the y. We took the whole function. We took the whole y value, made it negative. Okay. Well, if we have y equals 0, and I change the y equals 0, change the y between negative and positive, negative 0 is still 0. We're supposed to reflect across the x-axis, but the horizontal asymptote already was the x-axis. So the horizontal asymptote is still just going to be y equals 0. Okay, and so it was exponential growth. The base was 3, bigger than 1. It was exponential growth, and then I flip it upside down. Okay, I take this graph and I reflect it about the x-axis. So instead of going up here, it's going to go down. So I'm still going to have my horizontal asymptote on the left side, but instead of going like that, now I go like this. Okay, so let's take a look at a few more here. So let's say we've got 3 to the negative x. So my y-intercept, I can do 3 to the 0. I can get the point 0, 1. Okay. So this one, the only transformation we have is we have a negative on the x. So this one, the negative is inside directly next to the x. So we're going to look at the graph. We're going to look at the graph and we're going to change all the x's between positive and negative. And so if you change x's between positive and negative, you're reflecting about the y-axis. Okay. Well, let's think about a horizontal asymptote. So we had this horizontal line here, and then we reflect across the y-axis. So take the line and flip it across like that. It's still the same horizontal line, right? So we still have y equals 0 for our horizontal asymptote. Okay. Now the shape of the graph. So we could either think about that it was exponential growth, and then we reflect it across the y-axis. So take exponential growth and then flip-flop it across the y-axis. Well, if you take exponential growth and flip-flop it across the y-axis, what do you get? You get exponential decay. Let's take a look at this. What would be another way to write 1/5 to the x? That would be 5 to the negative x, right? Negative exponents would make those fractions. This thing right here, 3 to the negative x, well, negative exponent, that's 1 over 3 to the x. That's 1/3 to the x. So this is actually just our exponential decay graph, okay? So we're going to have this point 0, 1. And instead of having the horizontal asymptote on the left side, we're going to have the horizontal asymptote on the right side. And so it's going to look like that. Okay? So either think about growth reflected across the y-axis, or just think about your basic exponential decay graph. Okay? So then this one here, plug in 0, we're going to have 5 e to the 0. Again, make sure you do PEMDAS, make sure you do the exponent first, and then the multiplication. So and remember, e is just a number, and 2.7, anything to the 0 power, it's 1. So we're going to have 5 times 1. So we've got the y-intercept 0, 5. And so notice this number out front actually is our y-intercept. For an exponential function, if you just have a number out front, it's always going to be the y-intercept. It's the initial value. Kind of like in a line, y equals mx plus b. The plus b is the y-intercept, the initial value. For exponential functions, the y-intercept, the initial value is a number multiplied out front. Okay. Now, for your horizontal asymptote, well, it's normally y equals 0. And so if I didn't have that 5 there, it would be y equals 0. Well, now I took all the y values and I multiplied them by 5. Well, 0 times 5, that's still 0. So my horizontal asymptote is still y equals 0. Okay. Don't get thrown by the e there. Again, e is just 2.7. So e to the x looks pretty similar to 2 to the x or 3 to the x. This is just going to be exponential growth. It's just our basic exponential growth function. We just moved the y-intercept up a little bit. It's just kind of stretched a little bit. And so the graph looks like this. Okay. Again, don't get thrown by the e. This right here could be e to the x. So this point here was 0, 1. As long as I don't label any of the other points yet, that right there could be e to the x. Okay. Just if it's 2 to the x, we'd have the point 1 comma 2. If it's e to the x, we'd have a point 1 comma e. 5 to the x, we'd have a point 1 comma 5. But the basic shape of the graph would be the same. Okay. And so this one here, so if you have a number out front, it changes the initial value. If you have a number next to x, it actually really doesn't change much at all, because you could look at this as e to the 5th to the x. Well, e to the 5th is just some number bigger than 1. So this is actually just basic exponential growth. You're still going to have the point 0, 1. Try it. Plug in 0. You'll still get 1. And then that 5 is multiplied by the x's. The horizontal asymptote is about y. So it's not going to change. Right? This is something like somewhere between 32 and 243, somewhere between 2 to the 5th and 3 to the 5th. It's just some positive bigger than 1 number to the x. Just basic exponential growth. Just a little bit steeper. Okay? Again, 100 to the x would be steeper than 2 to the x, but they would still be the same basic shape. Something like that. Okay. So why don't you go ahead and try 7, 8, and 9 now. Think about where the y-intercept is. Think about the horizontal asymptote. Think about the shape of the graph. Make sure you account for any negatives, any kind of reflections that have happened, and give us a sketch of the graph for 7, 8, and 9. So your graphs should have looked something like this. All right. So for number 7 there, we had that negative on the outside. It reflected about the y-axis. All right, you can make sure you stuck the negative on at the end. For this one here, you could either think about it as growth that got reflected or just as exponential decay. You think about that as 1 over e to the x. That'd be a number less than 1. Or just think about e to the x and then flip-flop the x's between positive and negative, and you get this shape here. All right, this one, the asymptote did change because we went up and down. We'll change the horizontal asymptote. Over here, the +1 was a shift left 1, so that did not change the horizontal asymptote. All right. And then, so on this one here, so if you plug in 0, you should get 0, -1. Reflecting doesn't change the horizontal asymptote. It's the shape of the graph that you got to think about a little bit. Okay, so you could either say, all right, I'm thinking about e to the x. If I think about e to the x, I'm starting here, and then I have to reflect it both ways. I have negative on both the x and the y, so I would reflect it across the y-axis and reflect it across the x-axis. If you reflect exponential growth both ways, you end up with that shape of the graph. Or you could say that e to the -x is exponential decay, and so you could start with the exponential decay graph, and then from the exponential decay graph, reflect across the x-axis, make the y's negative. That negative out front would make the y's negative. So we could take exponential decay, change the y's between positive and negative, and get that graph. Okay. So one last thing to switch gears here, solving some equations. This is something that you should have done in Algebra 2, but with distance learning in the spring, it might have gotten skipped. And so what it is, it's a trick where you make the bases on both sides the same. Okay? You look for a way to rewrite both sides so that they have the same base. So the key here is that 9 is the same thing as 3 squared. So what we're going to do is we're going to write this as 3 to the x. We're going to rewrite the 9 as 3 squared. 9 and 3 squared are the same thing, so I can replace 9 with 3 squared. Okay, and then power to a power right here, an exponent on an exponent, we multiply. So that's going to be 3 to the 4x plus 2. Well, then if the bases are the same, that means the exponents have to be the same. So we've got x equals 4x plus 2. Subtract the 4x, negative 3x is 2, divide, and we get x equals negative 2/3. Okay. On this one, well, 8 can't be written very easily as a power of 4. 4 squared would be 16, right? I mean, you could do it. You could use a fractional exponent. You could think about maybe like square rooting 4 and then cubing it to get 8. You could make 8 be 4 to the 3 halves if you really wanted to. But typically what we do is we say, well, let's just change both of them. Both of them have kind of a common base that they could be rewritten as. Both of them could be rewritten as 2 to a power. 4 is 2 squared, right? And then 8 is 2 cubed. So I rewrite both sides so that they have the same base. Then power to a power, I multiply those exponents. So that's 2 to the 6x, and then that's going to be negative 3x plus 6. Let's make sure you distribute there, multiply the 3 by both of those. Then if the bases are the same, the exponents have to be the same. So 6x is negative 3x plus 6. Add the 3x over. Divide by the 9. We get 6/9, which of course simplifies to 2/3 again. Just a coincidence. It's not like every one of these problems is going to have 2/3 as an answer, right? Okay. Why don't you go ahead and try number 3 there. Write both sides of the equation so that both sides have the same base, and then solve for x. Right. So you should have gotten x equals 2 for number 3 there. Rewrite the 1/5 as 5 to the negative 1, 25 as 5 squared. Multiply those two exponents together, set the exponents equal to each other, and then solve. And then this one would have been pretty easy to check yourself. If you plug that back in there, 1/5 squared is 1/25, and then 25 to the negative 1 is also 1 over 25.